statist. Okay. Okay, so we will continue to write the integral representation of the partial sum functions. Okay, so okay, so we have okay, and here we know the coefficient of the constant term x by Euler's formula. It's this integral, and an. Okay. All right, and so last Thursday we have ended up with the following expression. Okay, and f of x plus t plus f of x minus t divided by 2, the dmt dt, and d sub mt is the Dirichlet kernel. Okay, and we have found a formula for this sum to be sine n plus 1/2 of x divided by 2 sine x divided by 2. Okay, if x is not equal to 2k pi, and the k is any integer, and the other is n plus 1/2 if x is equal to 2k pi. Okay. So we have, and so we can do the substitution of this formula because the integration interval is from 0 to pi, and as an endpoint, we may think about that the t is greater than 0, right? So that we can use this formula. By the way, sorry. Okay, I use this variable x. Okay. Okay, so after the substitution, okay, and so now the limit n goes to infinity because we want to answer the convergence problem. So for a fixed x in between minus pi and pi, we want to know that whether this limit exists or not. So n goes to infinity. Okay, so that so this is actually a limit n goes to infinity and 2 over pi 0 to pi. Okay, f x plus t f plus f of x minus t divided by 2, and we can do the substitution. So this is n sine, sine of n plus 1/2 of t divided by 2 sine t divided by 2 and dt. Okay, and then last Thursday we state that this limit is equal to this limit, okay, by replacing the denominator, right, with the function t. All right, so n plus 1/2 of t, and this is t dt. Okay. Right. Since, okay, so last Thursday we state that since that the difference of these two limits, okay, so the difference of these two limits one over t minus 1 over 2 sine 2 divided 2 fx plus t plus fx minus t divided by 2 and the sine m plus 1/2 t dt is 0. Right? Okay. Okay, to see this, right? So we want to, for next, we want to show that this limit is 0. As we have learned from the back, remember the back lemma, that if we can show that this function if we can show that if this function, okay, is absolutely integrable over the interval from 0 to pi, then of course this limit goes to 0, of course, by reading the back lemma. Okay, so we have to show that this one. Yes, please. Oh yeah, I'm sorry, because I should send you a lecture notes which will include a proof of the Raymond Black lemma.
Also, it'll come with.
Yeah, come with the lecture notes. I'm sorry. Yeah, I haven't sent the note to you. Yes. Okay, so so to this relate because GT to be a function like this one. Okay, all right, and because that we should exclude t equals 0. So if t is between 0 and pi, but exclude 0, okay? And if, how about t equals 0, then we can arbitrarily define to be 0, all right? And the reason, as we have understand that this function, the denominator, will very close to t when t is quite small, okay? So this is just a definition, okay? Because for every t greater than 0, this is well defined. And for t equals 0, just assign a value for that, all right? So gt is its function. And we can see that this function, which is continuous, okay, near pi, okay. The reason is that if you take the limit, right, the right limit of g of t, so this is for t, so this go down means that t is positive but going to 0, okay? So if you check this limit, you will see that this is equal to 0 and this is t of 0, okay? Right, and so I ask you to compute this limit, okay? Because I have given you this formula already, right? So I ask you to find this limit. Okay, so it's just a practice of limiting process you have learned from calculus. Yep. So I'll skip the detail. So this is a continuous function, right? So g of t is a continuous function. Okay, and as a continuous function on a bounded closed interval, okay. So and then right is bounded okay, on this interval, i.e. there exists an n greater than 0 such that g of t, okay, such as g of t is less than or equal to n. Okay. I think that there is a name of this factor in calculus. I forgot at this moment. Okay, but actually, okay, what was the name of the theorem? Anyone of you remember that the property, a continuous function on a finite cross interval, okay, is bounded, means that you can find, okay, so you can find bounded means that okay, maybe I will say that. So, and they are A, B, U. Are such that GT is upper bounded by B but lower bounded by A for all T in real pi. Okay, so this is a general property for a continuous function on a finite cross interval. Okay, so which means, for example, if we have say zero and pi, right? And because it's continuous here. Okay, so it has a maximum value. So this is B, and we have a minimum value A. And this is G of T here. Okay. Yes?
It's just called the boundedness theorem.
Boundedness theorem in your calculus textbook.
From our notes, but I think it's
Yeah.
It's a common name.
Common name?
It states that, it states that if f of x is continuous on the closed,
Finite cross interval, right?
then it is bounded on that interval.
Yeah. So you can find A and B. Okay, so that G function has a maxima, attain a maxima in this interval, and also attain a minima. Okay, so that the equality, you have equality, all right? So B is the maxima and A is the minimum. Okay. Yeah, in analysis, this is called the compactness property. But but anyway, boundedness theorem, I think it's not a good name because I know there's one name which is very good, but I forgot right now. I forgot. Okay, so anyway, so this is a fundamental property about continuous function on a finite cross interval like here, 0 to pi, all right? And so it has a maximum and also a minimum here, okay? And so that thus G of T is bounded 0 pi, okay, i.e. they exist, yes? Yes, extreme value theorem, yes. Thank you. Yeah, this is the good name. Yeah, so extreme value theorem, I say by the extreme value theorem for continuous function on a finite closed interval. Okay, so extreme value theorem, very good name. Yes, and so that because A, B can be positive or negative, but however, you can know that it's bounded, which means that there is an n greater than 0, such that we will take the absolute value can be upper bound by n, okay, for all t e pi. Okay, so that and so now if we look at okay, so that now we want to show the function in this box is absolutely integrable over the interval from 0 to pi. Okay, so we have here, and because that, so this is actually g of t divided by 2, go here, okay, and as we know, it has a bound, so this is, so we can replace the absolute value of the g function by n. Okay, and again, okay, and dt plus E2. Okay, so we have the splitting here, and we just do the integration here. So and remember that f function is a periodic function with period 2 pi. Okay, with 2 pi. So that's we can actually so we can do the following thing. This is 2 pi. Okay, and we can, first of all, we can do the change of variable. So we can say y equal to x plus t. Okay, right, for this one, and y equal to x minus t for this one. All right, and so that so t from 0 and x plus pi and f of y. All right. and dy. Okay, what's more? Plus, and here, this is f of y, okay, and minus dy, okay, and this one is x and x minus pi from here. Okay, is that right? Okay, good. Now, because this is minus pi, so we just flip over the two numerator. Okay, so this one goes to x minus pi to x. Okay, and dy. Is that okay? All right. And so you combine together, so you get a divided by 2, and this is x minus pi to x plus pi, and f of y, and dy. Is that okay? But as you know, x minus pi to x plus pi is a period, is a term of length to pi, right? So this is actually a period, and a periodic function, so this is actually the same thing, okay? But we know that the periodic function is absolutely integrable, right, over one period. So this is already finite. So you can see that this integral, right, x finite, right, so that 1 over t minus this function is absolutely integrable, okay, over this interval. And then by Riemann Lebesgue lemma, okay, this the limit it's 0. All right. So we have shown that the equality actually holds, right? All right. So we have this integration. Okay. So now we are able to conclude the convergence problem, and in the following theorem, 11.1.b, right? We call Riemann's localization theorem. Okay. Okay, so let f be a periodic function with a period to pi which x absolutely integrable over the closed interval from minus pi to pi. Okay, then the trigonometric Fourier series generated by f, okay, will converge, all right, for a given value x in the finite closed interval from pi to pi, if and if for some delta less than for some delta, for some positive delta less than pi, the following limit exists. Okay, so that limit n goes to infinity to over pi from 0 to delta, and the f of x plus t plus f of x minus t divided by 2, and the sine n plus 1/2 of t divided by t dt. Okay? In which case, the value of the limiter, okay, is the sum of the trigonometric Fourier series at x. Okay. All right. So to see this, we look at here. We can select a delta, right, which is greater than 0, but less than pi. Right. So it's actually, if we can write down, so this is actually a limit. N goes to infinity, right? So we can break down okay, this one plus from delta to pi, okay, and okay, right. So the integral. So basically, all right. So we break down the integration interval into two pieces. Okay, and the delta is select arbitrarily in between 0 and pi. Okay, and So what do we do is to show that when n goes to infinity, the second integral goes to 0. Go to 0. By what? Again, by the Riemann-Lebesgue lemma. Okay? So a proof is quite similar to the proof of here. So we will show that. So the proof here. Yes. Double. Which one? The following limit. Hmm?
The left end of the line.
Yes, please.
This is an if only.
Oh yeah, if and only if, yeah.
So
It's a notation for if.
if the first condition is
Yeah. Okay. All right. So, okay. The first statement, the trigonometric Fourier series converge for a given value, which means that this limit exists, right? This limit, because the limit of the partial sum function, okay, has been shown to be the limit of this integral. Okay, so that the trigonometric Fourier series converge at an x in between minus pi to pi, if and only if this is true, right? If only this limit exists. Okay, and so before we show that, we let this term to be 1 over t. So f of x plus t plus f of x minus t. Okay, we define for all t in delta and pi. Okay, is that right?
this is the proof of the theorem.
Yeah, the proof of the theorem is yes. So anyway, maybe I say here. All right. I just stated. And note that the function h of t, the function h of t equal to 1 over t is continuous. Okay, delta to pi, right? The inverse 1 over t, right, is a continuous function on this interval. And then, by the extreme value theorem, okay, so by extreme value theorem, h of t is less than equal to m. Okay, but actually we can say you can assign m to be 1 over delta, right? Because this function is mountain decreasing, okay? So the maximum value should be the value at the endpoint at delta, right? So that you can select m to be 1 over delta, right? So for all, and it, of course it's always positive, so for all t in delta pi. Right. So that if we integrate delta to pi, and if we 1 over t over 2, right? So when we do the integration, then we know this is all right. So it is not necessary to, actually it's not necessary to apply the extreme value theorem because this is a very specific function, right? So you just know this is a mountain decreasing, and so the value, the 1 over t has a maximum value when t equals to delta. Okay, so you're not necessary to apply. I mean, this is a big theorem, but in this case, you don't need to do so. Just look at it. And then you can, if you extend this time to the bigger interval, because this is an integration is from delta pi, right? But if when you extend it to 0 for the low limit, okay, because the integrand actually it's a magnetic value. So again, you have here, and as we have derived here, okay, as you can see, right, this one, okay, go over, so you can see this one, go over, now we have this, the same integral, and when we go over this one, we know that this is derived again, right? So it has an upper bound like this one. And so this is finite. Okay? And the procedure similar to previous derivation. Okay? As here, because that in here we start with this integral, right? From 0 to pi, right? And we end up with an upper bound. Because the upper bound, when we split this sum, we have these two terms. So we have by triangular inequalities, we have an upper bound, and then we, as this process, we find that we end up with this upper bound. Okay, so this function, this integrand is absolutely integrable. So by Riemann, Lebesgue, Riemann, okay, the limit n goes to infinity, pi delta to pi, and f of x plus t plus f of x minus t divided by 2, and the t sine m plus 1/2 of t dt is 0. Okay, so we have shown that as n goes to infinity, the second integral goes to 0. So this limit, right? So So this shows that the limit of n goes to infinity to divided by pi, 0 to pi, f t x plus t plus f minus t divided by 2 sine n plus 1/2 of t divided by t. So this integral, the limit of this integral, and you see the integral has integration interval from 0 to pi, is equal to the limit n goes to infinity pi. And delta and 0. Two sine okay, and so the limit n goes to infinity xn of x, right? So the limit of the partial function is equal to the limit of this integral, and also is equal to the limit of this integral. And because delta can be selected as very small, right? So delta can be very small. All right, so the convergence property of the partial function at x depends on the behavior of the function, okay, of this function, of this sum, when t is very close to 0, right? So it's localized 0. And when t is close to 0, so the argument is very close to x, right? Okay? So the convergence property of the partial function depends on the behavior of the function f, the periodic function at x. Very localized, a very local property of the function f x. So this is called the Riemann localization theorem because it's very localized. Okay? And as you can see, when t goes to 0, the function goes to what? Goes to a limit. What is this limit? You can see as t goes to 0. So what is this? Yeah. Good. It's n. That's right. You can apply L'Hopital rule, right? Because as t goes to 0, numerator and denominator goes to 0 simultaneously, right? In this condition, you can apply L'Hopital rule by doing the differentiation. Okay, so when you do the differentiation, this is become 2 cosine n plus 1/2 t, and this is 1. Okay, and when t goes to 0, cosine function goes to 1. All right, so this is n plus 1/2. Okay, so you can see the behavior, you see, and this is a continuous function. Okay, and so this part as t goes to 0, then it is equal to this one. Okay, right? So this is localization. Okay, and as delta is very close to 0, right? The integration depends on the behavior of f at x, because t is very close to 0. So f of x plus t is it's about f of x, and this is also about f of x, the value. Okay, and you take the average. Okay. Okay. Okay, so the convergence, this convergence problem, right, can be answered by the behavior of the periodic function f of x at the x, at the point x. Okay, so I would like you to know why the theorem is called localization theorem, very localized. Okay, so that we have even one if condition. Any questions? So at this moment, you can see the special feature or special property of the trigonometric Fourier theory generated by periodic function f. Okay, and its convergence problem can be answered by the local property of the periodic function f itself at every point x. Okay, at every point x. All right, so let's take a break up to 2:20, okay, about 5 minutes.
So after we done this,
Mhm.
we change it into this, and then we take delta close to 0. But if we want to,
No, not necessarily.
yeah, you pick a small enough delta. That's what you do, right?
Yeah, so which makes that you can select any data in between 0 and pi. All right, so you can replace the.
But you want it to be close enough to 0. Maybe
But yeah, but data never 0.
yeah, but so we need a limit, right?
No, but I don't. I don't need.
You don't need.
Yes, because we just need to evaluate the limit as n goes to infinity, which means that as the angle frequency of the sine function goes to
When
infinity.
you're picking a small enough delta over here, you need the limit.
But the limit, if exceeds, were independent of the data is selected, unless data is in between 0 and pi. Data can be any number between 0 and pi. Right? So if, for example, if your data is like, say, 1/2, okay, and then you evaluate this limit, and you find that this limit exists, say, some number a, okay, then you replace, then by meaning the big lemma, delta, if you change the data to 1/3 or 1/4, right, then you get the same limit.
So the process that you change delta from 1/2 to 1/3 to 1/4.
Yeah, never mind.
It's taking a limit.
No, no. Delta can be any. The statement.
Yeah, delta can be anything
yeah.
between 0 and pi.
Yep.
Right? But if you need a small enough delta, then you need the limit of it.
All right, so I will continue to, so you can see that indeed this limit, if it exists, does not depend on delta you choose. Okay, the only requirement is that the data should be between 0 and pi. Okay, it's in between 0 and pi. This is the only requirement you need. Okay? Okay, so we want to, okay, here. Right, so consider a fixed x in the corresponding cost interval from minus pi to pi, and any positive delta less than pi, right? And then we let a function little g t with parameter x. So it's a function of t with parameter x. So this is defined to be this average divided by 2. Right? And this function is defined from 0 to delta. Okay? So we just see the local behavior of a function f because x is selected, is fixed. So when t is in this small interval, then you can see this function, the behavior of this function g is determined by the behavior of the function f at y, at x, 1x. So you see that the argument here is from x to x plus delta, and here is from x minus delta to x. Okay? Right? Alright, so now the integral in the Riemann localization theorem becomes pi over 2 t 0 to delta, and the g function t over x, and the sine m plus 1/2 of t divided by t, and the dt. Right? So this is the integral we will have. And this integral, which is famous in the mathematical community, which is an instance of the Dirichlet integral. The Dirichlet integral take the form like here, from 0 to delta h of t, and the sine alpha t divided by t dt. For alpha greater than 0. Okay? And this is for any absolutely integrable function h defined on this small interval from 0 to delta. Okay. So this is a general formula of the Dirichlet integral is here. It's a function h of t which is absolutely integrable over this small interval from 0 to delta. All right, and this kernel, okay, and this function here. Okay, now And so by the Riemann localization theorem, the following limit alpha goes to infinity h of t, right? So if we want to evaluate this limit, the Dirichlet integral, as alpha goes to infinity, okay, then the following limit, if it exists, this limit may not exist, but if it exists, okay, it's the same. Yep. dt. Sorry. So it's the same for all positive delta less than pi. Okay. So let's take an example, very simple example. So let h equal to c. So h is a constant c. Okay. Okay. Then we evaluate alpha goes to infinity. And this is the limit alpha goes to infinity. And we have 2c divided by pi. 2c divided by pi. Okay. And it's 0 to delta sine alpha t, t, and dt. Now we do the change variable, okay, to evaluate this integral. So the change is that we let u equal to alpha t. Okay. And because alpha is going to infinity, so we can think about that alpha is positive. Okay. All right. So that du is equal to alpha dt here. Okay. And so this is the limit. Alpha goes to infinity. Okay, and so you can think about that this is alpha here, and this is alpha here. Okay, so now we have 2c divided by pi. Okay, and u is alpha delta and 0, and sine u divided by u and du here. So now as alpha goes to infinity, the upper limit goes to infinity. So we have improper integral. Right? And this improper integral, the improper integral 0 to infinity sine u du, which is the limit of b goes to infinity. Okay, this limit is actually equal to pi over 2. Okay, and the evaluation, I ask you to find from a table of integral, or you can find it by using Google search, something like that. But I give you a reference, okay, so you can see how to evaluate this one. But actually, it can be evaluated, okay? Because this is a so-called sinc function, right? And the sinc function, okay, so later on we will have it has a Fourier transform like a rectangle, functions, okay? But I thought it can be obtained by using a Fourier transform. Later on we will discuss that, right? But at the moment, because this is a very special function here, okay? So in mathematics it's called the sinc function, and the value is pi over 2, right? So the equation you can see the sinc function is just like a okay, all right, and its maximum is 1. So the sine u divided by u here, all right, so this is okay, so that is up, down, but the ripple become smaller and smaller, okay? Because what? Because the numerator upper bounded by 1, but the denominator when it goes up, so the envelope goes inverse proportion to u. Okay, so going up, and then if you integrate the area here, you can right. Okay, so you see that this area is bigger than this one. This area bigger than this one. Right. So this is a plus. This is a minus, plus, minus, right? The overall area, okay, after you do the integration is pi over 2, a magic number here, okay? So this is pi over 2, and so that, okay, so this is 2c pi times pi over 2. So what happened? What is the result? What is c? So it recover the constant function that we see here. Okay. Okay. So you have a very interesting result here. Okay. Okay, so now okay, so from the example above, okay, it is suggested that if the right-hand limit of the function h of t at 0, so what is that? Okay, so t is go to 0 from the right hand side. Okay, so t is positive, but going to 0. Right? So if the right hand limit of the h function at t equals 0 exists, then we have, right? So it is suggested. Okay, so we have the limit to equal to, Okay, so we can recover the value of a function at t equals 0, but actually it's the right-hand limiter. Okay, so this is equal to that if the limit exists. Okay, so if the limit of this integral exists, then we should have that. So this is suggested from the previous example. Okay, as we can see that. And so the following theorem gives a sufficient condition for the existence of such a limit. Okay, so it suggests that we have this result under the condition. First, two conditions that this limit exists. Second, this limit exists. But we still don't know when this limit exists, right? So we need a sufficient condition. And this condition is called Dini's theorem. Okay. 11.1.c, which is called Dini's theorem. All right, so let h be a function, okay, defined on a small cross interval for some delta equals 0. If h of 0 delta, real plus exists, right? So this is the first one we need. And the difference of the function h from this limit divided by t, not divided by t. Okay, divided by t is absolutely integrable over 0 delta. Okay. Okay, so as we know, because the h of t goes to the right-hand limit as t goes down to 0, because you see t is defined over 0 to delta. Okay, so t is defined on the right-hand side of 0. Okay, so as t goes down from delta to 0, right, we approach to this limit. And we want the difference, okay, the difference divided by t, because it's as t go to 0, this is go to 0 and this is go to 0. So as t goes to 0, we have 0 divided by 0, right? Okay, and when we have 0 divided by 0, then there are many things to happen. Okay, can be anything. But we require that it is absolutely integrable. Okay, and this condition guarantees that this limit exists. So it's a coefficient condition, right? Then we have the result, the limit. So this limit, okay. So this is the Dirichlet integral. Right, so this limit exists and also equal to the right limit of h at t equals 0. So the condition now is quite mild. So we have to, first of all, we need that the right-hand limit at t equals 0 exists. The second thing is that this function is absolutely integrable, right, over this small interval. So again, we require local property of the h function around 0, right? Especially the right-hand side of the 0, okay? Here, in this interval, okay? The data can be as small as possible, but never 0, right? Never 0, so you can select. And so it depends on the behavior, local behavior, okay? So once we have these two nice properties, then the Dirichlet integral has limit as alpha goes to infinity, and this limit is equal to this number, okay? Okay, and the proof, I will give you the proof in my lecture notes, so I will omit it, okay? So the proof, please see the lecture notes again. So basically, we will apply Dirichlet theorem to answer our question, the convergence problem as well as the representation problem, very soon. Very soon. So, any questions up to now? Okay. So at this moment, we already have a powerful tool to answer our questions. Right? If no, then I want to take a remark. Specific for our application, because now we have specific h of t, right? What is h of t? H of t actually is this one, is g of t with x as parameter. So we are okay considering this function of t, okay? Consider this function of t. Right? So the remark is that if the periodic function we considered, the polynomial f has the left-hand limit, f of x minus, which we know is that y go down to go up. Okay, so that y is from the left-hand side, okay, to approach to x. Okay, so go up. Y is less than x, so y go up to x, and see here, right? And this limit exists when I fix x. So this is called the left-hand limit. So if has the left-hand limit and the right-hand limit, x plus y go down to x, okay? Go down to x. At a point x in R, so if this is the case, then then g0 plus, okay, this is g function, okay. So this is the limit as t go down to 0, g of t, x. So this is okay, and this is equals to t go down to 0, f of x plus t, limit t goes down to 0, f of x minus t, here. All right, and by the substitution, okay, we let x plus t equal to y, so y equal to x plus t. All right, so the limit when y equal to x plus t and t down to 0, so y will down to x, right? And this is f of y. Okay, this limit. And for yeah, and this time for x equal to x minus t. Alright, so the limit f of y, so this is y will go up to x, okay? Because y always less than x, because t always positive, right? And go down to 0, so that y always less than x. And when t goes to 0, y will approach to x, so go up to x, okay? And what is that? So this is 1/2 of f, the right limit, okay, plus f, the left, so the right hand limit and the left hand limit, okay? Right? So when the periodic function f has the left limit and the right hand limit at the point x in R, then this function, the g function, has the right-hand limiter at the t equal to 0. Right? This exists and is equal to the average. Right? The average. Oh! Sorry. It's x. I'm sorry. So it's the average of the right-hand limits and the left-hand limits of at x. Yeah. Okay, so this is about, because we want to apply the Dini theorem, right, to the Riemann localization theorem. So the h function, h of t, in the Dini theorem is equal to the g function here, g of t. And our parameter is x. All right, and furthermore, if f has, okay, right, a left-hand derivative and the right-hand derivative at the point x, i.e., right, so we have to define what do we mean by left-hand derivative and right-hand derivative. Okay, and the true limit Okay. All right. So about okay, so the left-hand limit, we will say at x, right? So that t goes to 0. Okay, f of x minus t, okay, minus f of x minus and minus t. Okay, is equal to L, and limit t goes down to 0. F of x plus t minus f of the right hand limit equal to r. Okay, so the difference we use is for the left hand derivative, we use the left hand limiter. Okay? Right. So we have to make sure before we evaluate the left hand derivative and the right hand derivative. Right hand derivative. We have to make sure that the f function has a left hand limiter and a right hand limiter at the same point x. Okay. So you have to see that this limiter exists equal to L, and this limit exists equal to R. The reason why minus t is because that this is minus t minus 0, right? So that so we have this. Okay, so so this is the ratio we have. All right, so the two limits exist. Right, so furthermore, if we have these two limits, then for any epsilon going 0, there exists a delta going 0 such that fx minus t minus f of x minus divided by minus t minus L, okay? This one is, right. So this is the definition, the epsilon delta definition of limit, okay? So that this ratio minus the limiter, okay? We are less than epsilon whenever t is very close to 0, right? So we have that. So this is for all t, right, in between 0 and delta. Okay, and for this one would be f of x plus t minus f of x plus divided by p minus r less than epsilon. Okay? Okay. So if f has a left-hand derivative and a right-hand derivative at that point, then we have these two inequality for every t in between 0 and delta. All right, now, so in particular, all right, so in particular, there exists, okay, a positive delta less than pi such that, okay, so we can find a positive delta such that this ratio x minus t minus f of x minus minus t is less than L plus epsilon. Okay, plus epsilon by the triangle inequality. Okay, the difference is less than epsilon. So the absolute value of this term will be less than L the absolute error and the epsilon. And also, from here, the f of x plus t minus f of x plus divided by t, okay, is less than r plus epsilon. Okay, so this is for all t is in 0 and delta. Okay, for some epsilon greater than 0. Okay, so you can select an epsilon arbitrary because this is true for every epsilon, and so you just pick one. You just pick one, pick an epsilon. Okay, you just pick an epsilon so that you can find a delta which is small. Okay, which is small, then pi, and have this inequality here. Okay, now to apply the Dini's theorem, because we need two conditions, right? So the first condition for the Dini's theorem is guaranteed when what? So this can be guaranteed when what? When f has the left-hand limiter and the right-hand limiter. Okay, right? Okay, so we need so this is the h of 0 plus, right? So the right-hand limit at 0. And we know that the right-hand limit of g is equal to the average of the right-hand limit and left-hand limit of f at x here. And the second condition here, we want to show that this ratio is absolutely integrable over the small interval from 0 to delta. Okay, and so now we can, so since g of t x minus g of 0 plus x, so this is ht minus h0 plus, right? Divided by t. You want to know whether this function is absolutely integrable, okay? And so that this is what is that. Then by substitution, okay, by the substitution of the definition here, and by the substitution of this limit, okay, so we have 1/2 f of x plus t minus f of x plus divided by 2 minus f of x minus t minus f of x minus divided by 2. Okay. All right, so we have that. Oh, t. I'm sorry, t here. And because the plus, so this is minus t. Okay? Right? Originally, this is, okay, originally this is plus. Right? But I want to change because I want to use this, the definition of left-hand derivative and the right-hand derivative. Okay? So this becomes the difference. And next one. Okay? Right. So the absolute value of this function, okay, will be, so this one will be less than or equal to 1/2 f of x plus t minus f of x plus divided by t. Okay, this one. plus f of x minus t minus f of divided by minus t. Okay? So the x value, okay, is less than equal to the absolute value of this term and plus absolute value of this term. And as we know, the absolute value of this value has upper bound here. Alright, so this is what is L plus NR divided by 2 plus epsilon. Okay, so for all t is 0 and delta. Okay? Huh? Oh yeah, thank you. Less than equal to. Thank you. So we find upper bound, right? We find upper bound for the absolute value of this function for all t in between 0 and delta. Okay, and this is constant, right? A constant, of course, is absolutely integrable, so that if we evaluate right, the absolute value of this function, so this is equal to, less than equal to here. Okay, so what is that? This is delta. And this is finite. Okay? So the condition that f has left-hand derivative and right-hand derivative is sufficient to guarantee that, that this function is absolutely integrable over an interval from 0 to delta. Okay? Yes? Which one?
The third line of
Oh, yeah. Sorry. Okay. Yeah. Okay, thank you. Okay, so this is implies that g of t x minus g of 0 plus x divided by t is absolutely integrable over 0 and delta. Okay. All right, so our focus will on a class of periodic function which has, first of all, left-hand and right-hand limits at every point x, right? And which has left-hand derivative and right-hand derivative at point x. Okay. So now we define such functions. A function f defined on a finite closed interval A to B is called piecewise continuous. Right? So it's called piecewise continuous. If there exists a final number of points A, so endpoint A is defined to be 0, x0, x1, up to xn equal to b, such that f of x is continuous on the open interval from xi minus 1 to xi for each I, and I from 1 to n. Right, and the left hand and the right hand limit, say f0. Alright, so for the endpoint A, we have the right hand limit, but for the intermediate point, we have left hand and right hand limit. So f(x1) minus f of x1 plus f of x minus 1 minus f of x minus 1 plus. And the right end, we have the left hand limit exists. Okay, so this is called piecewise continuous. Okay, so an illustration of a piecewise continuous AB. Okay, so A is equal to x0 and B is equal to xn. So we can find, say here, so this is x1, x2, x3, x4, and B is x5, for example. Okay, so we can divide the defining interval into 5 pieces. 1, 2, 3, 4, 5. There are 5 pieces, okay? And in each piece, excluding the ending point, the function is continuous. So the function would be continuous. That's what we mean. Let me draw that the function is continuous. Okay. Okay, so now excluding the endpoints, that in each subinterval, subopen interval here, the function is continuous. But at every point, the left hand limit and right hand limit exist. So you can see that at the x0, the function has what? Has the right hand limit. Okay, because when you approach to that, you have this one. Alright? And at the x1, it has left hand limit, also right hand limit. But these two limits may be different, right? In this case, they are different. Every point there. And the definition at the point can be like here, so maybe here, maybe there, or maybe just here, okay, or here, okay, or maybe there, here, okay. So the value at every point can be arbitrarily assigned here, okay. So this function, okay, is called a piecewise continuous function. Okay, so it's called a piecewise continuous function. And many functions in electrical engineering is piecewise continuous. For example, the clock signal, okay, and the many control signal in circuit theory, right, like a step signal, 0 and 10 ohm, okay, so that it has discontinuity at the time 0, okay? But, well, you can see that except the turning on time, that they are continuous, right? All right, so this is called the piecewise continuous functions. And it is clear that so it is clear that a piecewise continuous function f on a finite cost interval is absolutely integrable over AB. i.e., so this integral is finite. Okay, so I'll stop here, and on Thursday I will state our main theorem in this section, all right, to answer the two problems, the convergence problem as well as the representation problem. Okay, so any questions? Okay, if not, then I'll see you on Thursday.